Hello, everyone. This is the lecture for Monday, April 12th, 2021, coming at you live from Indianapolis, Indiana. At least it's live for me, but probably not for you. In fact, certainly not for you. But I'm sorry to just kind of get this lecture into the can, but I did think of a way to explain this that I think you'll be more inclined toward than what I was going to do. So hopefully you will agree as we go through this. We've been talking about vector fields. We've been talking about all aspects of vector fields. We've been talking about curl and divergence, line integrals, which, as you know, I'm inclined to call curve integrals. We just finished talking about the fundamental theorem for line integrals, which in particular told you what to do in the case of a conservative vector field, and that actually the path itself does not matter, only where it starts and where it ends as it pertains to work integrals if the vector field in play that's moving the particle along is conservative. All that matters is the beginning and the end. You take the potential function at the end and you subtract the potential function at the start, and you will get the work in moving the particle from the beginning to the end. But what do we do about line integrals in the case where the vector field is not conservative? Well, there's a couple of options. One is you can just go ahead and parametrize the curve and do the work integral in the way that we have done it before. Just straight up parametrize the curve and then evaluate the work integral the way that we have before. But there actually is an alternative to that in the case where you actually have a closed curve, a simple closed curve. Simple just means the curve doesn't cross itself, okay? Turns out that there's an alternative to how one goes about actually computing these things, and that is something called Green's theorem. Now remember, if the vector field were conservative, then the work integral around a closed curve is going to be zero, okay? Zero, it's just trivial. But it turns out Green's theorem gives it an alternative way for us to compute work integrals around a closed curve that doesn't cross itself. So it begins and ends at the same place. And the vector field doesn't have to be conservative, okay? So let us kind of look at exactly what's going on in this case. All right, here we go. We're in the whiteboard mode here. And let's look at what's going on. So remember the fundamental theorem for line integrals, FTLI. Fundamental theorem for line integrals says that the integral over C of a conservative vector field, which by the way is going to be the gradient of some potential function dotted with dr, is equal to f the end of C minus f of the start of C. Okay, we've kind of beat that one into the ground at this point. We even verified why that happens to be true. Okay, so an immediate corollary to that is that if you have a closed curve, okay, remember we kind of indicate that with that little circle shape right there, the integral of over any closed curve. So this right here just means that C is closed. Okay, that means it starts and ends at the same place. Okay, f dotted with dr is equal to 0. Okay, because the ending and the beginning are the same in that case. And so when you take that difference, you will obviously get 0. All right, so let's look at Green's theorem, shall we? Okay, so Green's theorem says that if you have a simple closed curve, so simple again means it doesn't cross itself, okay? It doesn't cross itself. So first of all, let's let f be a 2D vector field. Okay, so f is a two-dimensional vector field, okay? We'll have something else that we can do in the case of three-dimensional vector fields, but Green's theorem deals specifically with two-dimensional vector fields. And please, let's just call this, instead of M and P, I'm going to use P and Q, because it seems like I always get confused and then end up switching over to something else. P and Q, it's in alphabetical order right next to each other. I'll just use P and Q in this particular case. Okay, so F is a two-dimensional vector field. Okay, C is a simple closed curve. Simple closed curve with, okay, and I'm going to throw out one more word in here, with positive orientation. Positive orientation. Okay, what does that mean? Well, that means that the region enclosed by C is always on the left as we move in the direction given. Okay, because you're always going to have two options for how you go around C. And if you go around in the one direction, the work is going to be one number. If you go around in the opposite direction, the work's going to be the opposite number. Okay, so this thing is with the positive orientation. Okay, then here's kind of the kicker. The integral, so let me actually draw a picture of like a simple closed curve over here with positive orientation. Okay, so positive orientation means the region enclosed by this thing. So here's C, and I'm actually going to say, okay, here is the region enclosed by C. Okay, then what? After all that set up, the integral over C, and by the way, sometimes when we want to indicate positive orientation, you can kind of put an arrow like this. It's kind of going in the counterclockwise direction. And what that means is, well, I mean, look at that little circle. The region is always on the left as you traverse in that direction. Okay. F dotted with dr. Remember, if F was conservative, this would be 0, but we're not going to assume that F is conservative in this particular case. Well, it turns out that this is going to be equal to the double integral over R, okay, the region that C actually encloses, of what? Of the x derivative of the second coordinate function, Q, minus the y derivative of the first coordinate function, P, dA. All right? So what this does is it says, look, if you want to compute the work integral for this vector field around this curve, then as an alternative, you can just compute the double integral over the region of this difference between partials, the x derivative of Q and the y derivative of P, the x derivative of Q and the y derivative of P. Okay, so that's interesting. And by the way, remember, there's this alternative way to write the work integral too. Go like this, integral, and I'm even going to keep this on here, over C P dx plus Q dy, right? We've kind of talked about that as well, but that's kind of an alternative notation for these work integrals. Okay. All right, so hopefully that kind of makes sense. And by the way, let me just, the statement of this makes sense. Let me just say that sometimes you, instead of like writing C and R, sometimes you can actually replace, you'll see this in notation sometimes, you'll replace C with something like this. You'll write this symbol R, okay? And that stands for the boundary of R. Okay, so this right here is standing for the boundary of R, just so that you don't have to like make up lots of different letters for whatever it is you're talking about. So that little del R symbol, that just means the boundary of R. Okay, I'm going to keep the C in there just because we kind of understand what C is in this particular case. But yeah, that's just an alternative way to write things. All right. All right, so let's go over to the next page, and we're actually going to give an argument for why this happens to be true. Okay, So again, let me just rewrite what the statement of Green's theorem is. Okay, it just says that the integral over C of f dotted with dr, or let me write it this way. Let me write it with the p and the q in there, of p dx plus q dy is equal to the double integral over the region contained within the curve, q sub x minus p sub y dA. You might say to yourself, why in the world would I want to compute a double integral instead of just parametrizing the curve and dealing with it the usual way? Well, sometimes parametrization is very difficult. In fact, it might be impossible, okay? And so we've kind of swapped out this work integral for something that we've spent a fair amount of time dealing with in this case, or in this class, namely a double integral over some region in the plane. And actually, that double integral might be super easy, okay? It might be really, really easy to deal with, okay? So let's actually try to, here, I'm gonna draw a picture of a particular situation that we're gonna deal with. We'll establish why this is true in this particular situation, okay? So here's the picture I'm gonna draw. Suppose this is A right here, and this is B, okay? And I'm gonna imagine that our curve is like this. Okay, it's kind of a straight line piece over here and a straight line piece over here. And by the way, it's going to look like I'm really making a lot of assumptions, but it turns out that we're really not assuming that much. We can always break up regions in this way and kind of force things to work out eventually. So what I'm doing here might look like I'm assuming a lot, but it's really pretty general, okay? Okay, so look, I'm going to assume that this is the curve that we have, okay? And we want the region bounded by this thing to always be kind of going in this direction, okay? So here's our curve, C. That's the whole thing, okay? But as you can see, C is really built from a whole bunch of other smaller pieces, okay? I'm going to call this down here like C1. I'll call this piece right here C2. I'll call this piece right here C3, and I'll call this piece right here C4. Okay, and here's our region that is bounded by this curve right here. So we're just going to assume that this is the situation we find ourselves in. Okay, and I also want to assume something else, namely that this bounding curve right here is given by y equal to g2 of x. Okay, so this is given by some function of x, and that this curve right here on the bottom is given by y equal to g1 of x. Okay. All right, interesting. So to show this, we're actually going to show that when we think about all of these separate curves, so in some sense, right, what is C equal to? C is equal to like C1, remember we've done this before, plus C2 plus C3 plus C4, okay? So C1 plus C2 plus C3 plus C4, and we could kind of break up the work integral over each one of those curves if we were so inclined, okay? So what we're going to do is we're just going to think about this work integral along each one of those curves. And in particular, we're just going to focus on the part that involves P. So we will look at the integral over C of P dx and show that this actually equals what? Equals the part of the double integral that corresponds to the y derivative of P with a minus sign, okay, is equal to the double integral over R of negative P sub y dA, okay? That is what we're going to show. You might say to yourself, oh man, but what about the other part? Well, turns out that the Q part can be done in a similar way, Okay, the Q part can absolutely be done in a similar way. So it's not like we're really giving away that much in doing it this way. Okay, we're just going to show that the P part works out. Okay, and let's see here. So what is, okay, so let's note. So note first of all, note firstly that the double integral over R of negative P sub y dA. Again, this is what we have right here. Okay, so what is this? This is equal to, okay, so look at this. If I'm going to double integrate over R, what's going on here? Well, the way that we've drawn this region, it looks like I should let X go between the numbers A and B, don't you see? Okay, so I should let AX go between the numbers A and B. So it's going to be the integral from A to B dx, okay? And then what about dy? Well, dy, so think about this for a minute. This is interesting. What's the deal with dy? Well, y is as X goes between A and B, okay? So if I fix like a particular X value somewhere in here, then Y starts on this lower curve and goes up to this upper curve right here if I want to find myself inside of that region. Okay, so in other words, the limits of integration for Y go from G1 of X up to G2 of X. Okay, then I have this thing, negative P sub Y. Okay, and P sub Y is a function that depends on both X and Y. Okay, interesting. Okay, so now what do we do? Well, seriously, the innermost integral that we have right here, look, we're being asked to do the antiderivative of negative the y derivative of P with respect to Y. What is the antiderivative of that? Well, excuse me, that's just what? Okay, well, this is going to be the integral from A to B. Okay, the antiderivative of negative P sub Y, well, that's just negative P sub Y. Or just negative P, actually. Okay? So after all, the y derivative is just that negative P evaluated between G1 of X and G2 of X dx. Okay? And what I mean by negative P, okay, so P is just a function of X and Y, don't you see? Yeah. And I mean to plug in here Y equal to G1 of X and Y equal to G2 of X. So it's going to be negative P of X, comma, G2 of X minus negative, which is plus P evaluated at X, comma, G1 of X. So look at what this is. In the end, this is going to be the integral from A to B of P of X, comma, G1 of X minus P of X, comma, G2 of X. You see? And this is all dx. Okay? So in other words, this is what we end up getting. Okay? We end up getting this right here. And that's equal to this double integral with this piece of y thing sitting there. Okay? So that's cool. Okay, so we have P of X, G1 of X minus P of X, G2 of X. And that's what we get integrated from A to B in X. That's what that double integral over R ends up being. Okay? And now what we're going to do is we need to concentrate on what this actually is, what that thing actually is. Okay? So let's file this, this first computation away in our memory. We'll come back to this later, but now I want to do this line integral. I want to do this little line integral that we have going on right here. Okay. All right. So let's do that next. Okay. Okay. So here we go. What do we do next? Well, I want to compute the integral over C of P dx. And as you know, this is going to be the integral because C was like the sum of all those things. Okay, so integral over C1 plus the integral over C2 plus the integral over C3 plus the integral over C4. Okay. Well, okay, let's kind of look back at what C1, C2, C3, and C4 actually were. C1 was the bottom part. C2 was the part that was going up. C3 was going over, and C4 was going down. Okay. Now, let me ask you a question. If I were to compute the integrals along C2 or the integrals along C4, what am I going to get? Well, x is just a constant there, okay? So dx, think about it for a second. X is just, like if I'm going along C2, x is b all the time. So dx is just going to be 0 if we parametrize that thing. X is a constant equal to b every time as we're going along C2. As we go along C4, x is equal to a all the time. So dx is going to be 0 if I'm on C4. So the integrals along C2 and the integrals along C4 are both 0. Don't you see? Okay. So let's kind of think about this. So note, let's just kind of write down a little note right here. Note, x is always equal to b on C2, and x is equal to a all the time on C4. So dx is 0 on each of these. So that means that the integral over C2 of p dx is equal to the integral over C4 of p dx, which is 0. Okay. So that one was kind of easy. But what about C1? Well, we have to parametrize C1. Okay. C1, how are we going to parametrize that thing? Let me go back for just a second again, okay, to what we had before. C1, let's see here. How would I parametrize C1? Well, I can basically parametrize C1 by letting x go between a and b, and then y is just equal to g1 of x, for crying out loud. How easy is that? Okay, so look at that. X just simply goes between a and b. And as that's happening, y is equal to g1 of x, and that gets us on that curve C1, the bottom curve right there. Okay. So this is how we're going to parametrize this thing. It's going to look kind of funny, but C1 is just, x is going to be itself. Okay. And this is for a equal to or less than x equal to or less than b. And what's y going to be? Well, it's going to be g1 of x for a equal to or less than x equal to or less than b. Okay, so g1 of x. It's that bottom curve. Okay, so then what do we get? Well, the integral over C1 of p dx is equal to, well, what is dx? Well, x is equal to x in this case, so dx is just dx. Okay, this is going to be the integral from a to b of what? Well, remember p, don't forget, p is just a function of two variables, x and y, correct? And I have to replace y by what it's equal to. Okay, so x is going to go between a and b. Dx is just dx, and it's going to be p with x replaced by x and y replaced by g1 of x. And this is dx. Okay. Now, what about C2? What about C2? Well, C2 is a little bit more interesting, okay? So C2, what's going to happen with C2? Well, let's go back to the previous page and just stare at that for a minute. Look, remember, or not C2, C3, I'm sorry. Okay, not C2. C3, of course, the integral along C2 is 0. C3, excuse me. Okay. So what about C3? C3 is this curve that's going along the top. And it goes from right to left. It goes from right to left. So X is going from like B to A in this particular case. Okay. X is going from B to A in this particular case. How am I going to parametrize that? Well, let's just kind of think about that. Okay. So I can just straight up do it. I can say, I could just let X be X. Okay. And I could let Y, of course, to get up on that upper curve, Y is always going to be equal to G2 of X. And this is going to be X going from B to A. X from B to A. Okay, X is going from B to A in this particular case. All right, and that's going to look kind of weird because B and A are, I mean, because A is actually smaller than B, but that's okay. We would just integrate from B to A. So what do we get? Well, the integral over C3 of P dx is going to be equal to the integral from B to A of what? Well, P of X, comma, G2 of X, because that's what Y is on this curve, dx, which of course is just the negative of the integral from A to B of P of X, G2 of X dx. Huh. So what do we get? So what's our conclusion? Conclusion. Well, the conclusion is that the integral over C of P dx equals the integral of what? Look at this. It's the integral of C1 plus integral along C2 plus the integral along C3 plus the integral along C4. But we already said that C2 and C4, if you integrate along those, you get 0 for both of them. And we just computed as much as we can without knowing anything else, like the actual function itself. We just computed the other one, don't you see? Yeah, we just computed that other one. So, so what? This is equal to, okay, what's the integral along C1? It's that guy right there, integral from A to B, that thing. So this is the integral from A to B of Px G1 of X. Okay, and then I can add in this other integral, the integral along C3 itself from A to B, but that comes with a minus sign. So minus Px G2 of X. Okay, and that's dx. And where have we seen that before? Well, for crying out loud, we just saw it back here, don't you know? Okay. Well, not there, the second one right here. Okay. We did the double integral over the region, and we ended up getting that was the integral from A to B, P of X G1 of X minus P of X G2 of X dx. Exactly what we have sitting right here. So this is precisely equal to the double integral over R of negative P sub Y dA. Amazing. Okay. Integral over C of P dx is equal to the double integral over R minus P sub Y dA. And we just did some basic parametrization and just thinking about things in that regard to come up with this. Okay. And like I said, you could do the exact same thing with the Q part to prove all of Green's theorem. So remember, the statement of Green's theorem said this, right? That the integral along C of P dx plus Q dy, it also involved that Q part, is equal to the double integral over R, Q sub X minus P sub Y dA. Okay? That's an amazing thing, for sure. It's an amazing thing. Okay, so let's look at some examples here. Okay. Let's see. How about this? Okay, so let's evaluate. So example, let's compute the integral of x to the fourth dx plus xy dy. Okay, and this is going to be the integral with positive orientation, closed curve, okay, where C is the triangular curve consisting of line segments from 0, 0 to 1, 0, and then to 1, and then to 0, 1, and then back to the origin again, okay? And here, so here, I'm just gonna draw a picture of that right now. So it's this, okay, so here's 1, and here's our curve right here. Voila. Here is our curve, okay? So it's that curve with positive orientation. Well, notice that if we were going to actually just do this the old-fashioned way, the way that we knew before, we would have to split this thing up into 3 separate integrals, don't you see? We would have to do 3 separate integrals along each one of those line segments, going down the y-axis, going over on the x-axis, and then along the diagonal, okay? Those 3 separate things would have to be done. But keeping in mind that we have Green's theorem in our back pocket, right? I'll call this P, and I'll call this guy Q right here. By Green's theorem, okay, let me call this region R right here. So by Green's theorem, so this is GT, Green's theorem, is a big deal. This is going to be the double integral over R of Q dx, or Q sub x minus P sub y dA, which, by the way, in this case, let's see here, we'll kind of think about this region here. What is the x derivative of Q? Well, it's y. And what is the y derivative of P? What is the y derivative of P? Well, it's 0, for crying out loud. How convenient. Okay. And let's see here. How are we gonna move around on this thing? Well, first of all, this line right here is the line y equal to what? Well, 1 minus x. Yeah, that's y equal to 1 minus x. That's what that line is right there. And how do I describe this region? Well, I can kind of get rid of that. I'm gonna go what? I'll let x go between the numbers. So it's going to be dy dx. Okay, what are the limits of integration? Well, x goes between 0 and 1. As x goes between 0 and 1, so give me any x value. Y starts at 0 and it goes up to the curve. Okay, so y goes from 0 to 1 minus x. Nice. Okay, so look at this. This is going to be the integral from 0 to 1 of what? Well, it's just y is the integrand, dy. So then it's 1/2 y squared, evaluated between 0 and 1 minus x, dx. Okay, which is given by, let's see here, it's going to be 1/2. I'll pull out the 1/2. It's going to be the integral from 0 to 1 of 1 minus x quantity squared dx. Okay. Then you have to do an antiderivative of this thing. Okay. So what is the antiderivative of 1 minus x quantity squared? Well, it's going to be 1 minus x quantity cubed over 3 times a minus sign. This is going to be minus 1/6 because it's 2 times 3. 1 minus x to the 3rd power, evaluated between 0 and 1. Which in the end, when you think about this for a couple of seconds, so if I plug in 1, I get 0, and it's going to be minus negative, which is positive 1/6. Okay. So we get 1/6. 1/6. 1/6. So that's a pretty nice little fact right there, don't you think? Okay. All right. I'm going to pause this for a minute because I want to pull something up for you to see. Okay. I wanted to pull up a little thing on the internet I'm going to show you here in closing in a minute. But one thing that's really cool about Green's theorem, okay, remember this right here is the statement of Green's theorem. Okay, so Green's theorem says this, okay? And the curve has to be positively oriented, which means the region it bounds is always on the left. So it has to be a closed curve. And if that is the case, then the two-dimensional vector field can be evaluated by looking at the double integral over that enclosed region R. Now, Green's theorem, so GT, let me just say this, GT can be used to compute the area of R, okay, if P and Q are chosen so that what? Well, think about it. If you wanted that double integral to just be giving the area of that region R, then you would just need Q sub X minus P sub Y to be equal to 1. Okay, so that P sub X, or sorry, Q sub X minus P sub Y equal to 1. Because then that line integral would just be equal to the area of R. Because then the integral with, over the curve with positive orientation, P dx plus Q dy would be equal to the double integral over R. See, Q sub X minus P sub Y would be 1. So this would be 1 dA, which would just be the area of the region. Okay, so this gives us a way to kind of turn a work integral into something that's actually telling us a geometric feature of a region right there. And it turns out this has been used to compute areas of fairly complicated regions. And there's even tools you can buy that actually use Green's theorem by kind of going around on the outside of the region along the curve. And you basically just compute the value of that work integral. Okay, so the mechanics of it are such that it computes the value of that work integral, and that will also be the area of a fairly complicated region potentially. So here are some popular choices. Here are some popular choices for P and Qs that will work. So for instance, let's see here. I had a few different ones written down. So like P equal to 0 and Q equal to X, that would work, right? Because then Q sub X would be 1 and P sub Y would be 0. Here are some other options. P equal to Y and Q equal to 0. That's another one, okay? Another one that's fairly popular is to take P equal to negative 1/2 Y. Okay, here's one that you have both things involved, and Q equal to 1/2 X, because then in each of these cases, notice that the X derivative of Q minus the Y derivative of P is 1. Okay, you might say to yourself, why on earth would you want to compute a work integral instead of like just computing the double integral itself and getting the area that way? Well, it turns out there are some cases where the area of that region is fairly complicated, and the work integral is kind of the way to go. Okay, so and one example of that I kind of want to give. One example of that is the area of an ellipse. Area of an ellipse. It's actually a fairly complicated thing to find the area of unless you have the tool of Green's theorem. So let's take a peek at that for a minute. Okay, so example, find the area of the ellipse x squared over a squared plus y squared over b squared equals 1. Okay? So that is, it's like this, okay? So maybe this is A and maybe this is B like this. So we have the area of this ellipse. Okay, not a very good looking ellipse there, but you get the drift, okay? Well, what we're gonna do is we're gonna think about this thing with the positive orientation. I want the area of the region that's bounded by that ellipse, okay? Well, to do that, I'm gonna have to parametrize this curve C, okay? So how do we parametrize C? Well, if you'll remember, one way you can do that is x equal to a cosine of t and y equal to b sine of t. Okay, for what? For 0 equal to or less than t equal to or less than 2 pi. It's just kind of like a squashed circle. Okay. And then what we can do is we can do our judicious choice of x and y. So we'll use the third option that we had on the previous page. We'll sort of take p equal to -1/2 y, and we'll take q equal to 1/2 x. Okay. Then the integral with positive orientation around C of -1/2 y dx plus 1/2 x dy is going to be equal to, after all, this right here is P and this right here is Q. By Green's theorem, I'm writing in green because it's Green's theorem. Okay. By Green's theorem, this is equal to the double integral over R of Q sub x, which is 1/2, minus P sub y, which is plus 1/2 dA. Which, by the way, is equal to, right? This is just 1 for crying out loud. That's just the area of the region, area of R. Okay. Well, let's see here. This is equal to what? It's going to be the integral from A to B. Well, actually not A to B. I actually know what A and B are. From 0 to 2 pi of what? Well, let's see here. -1/2 y dx. So this is -1/2. What's y? Y is -1/2 y. Y is b sine of t. -1/2 b sine of t. What's dx? Well, x is equal to a cosine of t. Don't you see? Yeah, a cosine of t. So dx is -a sine of t. Okay. Let's see here. Plus 1/2 x. Okay, so that's going to be 1/2 a cosine of t dy. Y is equal to b sine of t. So dy is going to be b cosine of t. All right. And this is dt when all is said and done. Okay. So what's that equal to? Well, think about it. Minus is plus for that first product. You can factor out the a and the b and the 1/2 from everything. Don't you see? Okay, so the a, the b, and the 1/2 factor out. So this is 1/2 ab, the integral from 0 to 2 pi. And then you have sine squared plus cosine squared, but sine squared plus cosine squared is 1. Amazing. And the integral from 0 to 2 pi of 1 dt, that's just 2 pi. And I divide that by 2 and I get pi. So look, we get pi times a times b. That's the area of an ellipse. You get the two radii for the ellipse, the major and the minor axis for the ellipse. And it's pi times each of those. And that makes sense even in the case of a circle, right? Right? If it was a circle, then a and b would be the same, and you would just get pi times the radius, which is pi r squared. So this is an extension of the area of a circle. Isn't that cool? So we used Green's theorem kind of in the reverse order from what you normally would to actually find the area of that ellipse. Okay. One more thing and we're done. I want to share my screen here and then we'll be done. Okay. Wanted to show you this picture right here. This is an article that came out not too long, or actually it's fairly old now, but there are still articles coming out. It's from the American Mathematical Society. And it's talking about this thing called a planimeter. It's a way of measuring area by tracing around the outside of a closed curve. Okay. And it talks about the reason that it works. There was a sequence of articles that does that. There's been a lot of obsession over this. It's really a pretty cool tool. Some fairly complicated regions, areas have been computed using planimeters. And the principle upon which all of this works is indeed Green's theorem. Okay. You basically are exchanging, having to like deal with the area of the inside of that region with a work integral along as one traverses along the curve on the outside, okay, where we've judiciously chosen a P and Q that make it quite easy to figure out what that work integral is. Okay, I think that's cool, and hopefully you do too. And that, my friends, is all there is for now. I will finish 15.4 next time. I think I might do one more example and we'll move into 15.5. So I'll post this lecture tonight. I'll post some homework for this as well, but that probably won't be due until the beginning of next week. And then I'll move into the 5th section of chapter 15 really soon, probably in the middle of this next lecture that I'll post after this one. All right, that's all for now.